welcome to tonight's North Essex Astronomical Society talk. It's on red dwarf stars. My name is James Hannon. I'm the chairman of the North Essex Astronomical Society, and this is a general talk about red dwarf stars, but it also sort of follows my journey when I ridiculously thought 2 years ago that I could do a part-time master's while also working full-time as a science teacher and assistant head at secondary school. Spoiler alert, I did succeed, and this is going to talk about the final project that I went through. I initially entered the master thinking I was mostly interested in exoplanets, and it soon became apparent that actually red dwarf stars not only linked to that but also were quite interesting. So this is about a general overview of red dwarf stars, and then I will talk about the research that I did. So I think it's probably best that we start off with what is a red dwarf star. And I think importantly, first of all, that a red dwarf star is exactly what it sounds like on the tin. Most of the time in astronomy and astrophysics, we try to keep it fairly simple. And a red dwarf star is a star that is red and it is small. It's no awards there for naming. So, but to go into a little bit more detail, we know that a star's size and therefore its temperature is linked to its colour. And here we can see we've got some black body radiation curves. And for example, if we look here at the sort of temperatures that our sun would be, around 5,700 Kelvin, or 5,500 Kelvin, we'd be looking at a peak here in the visible range. And so the colour here of the sun would be around that green-yellow border. Now, if we look at much cooler stars, which is what a red dwarf would be, it's smaller. It's like the opposite of your bathroom taps. The hot stars are red. Sorry, the hot stars are blue, and the cold stars are red. So here, if we look down here, about maybe around the 3,000 Kelvin mark, which is a good sort of temperature for a red dwarf, we can see here that the peak temperature at 3,000 Kelvin would actually be here in the infrared range. And so red dwarf stars peak in the infrared range. So let's have a look at a little bit more information about red dwarf stars. We classify stars based on their colour and their temperature, and we use this nomenclature here, OBAFGKM. Now the way we remember that in astronomy is O be a fine girl, kiss me, or O be a fine guy, kiss me. And so that's a good way of remembering it. And it obviously we would have originally started off with A, B, C, D, but over the years we realised that our scale was slightly incorrect. Numbers or letters merged together when we realised they were the same classification. And with the rearrangement we ended up with OBAFGKM. So the stars that we're mostly looking at here are in this region here, the K and M, but specifically I looked at the M-class stars. So if we look at our M-class stars, they are much smaller. They roughly around about 0.1 of the solar mass. You can see here that the temperature range is 1.5 to 8 times 10 to 29 kilograms. As a comparison, the sun is about 1.99 times 10 to the 30 kilograms. So you can see there is a difference there about 10 to the 1. So if we look at these red class stars down the right hand side here, we can see we've got Proxima Centauri, Barnard Star, Wolf 359, and so on. The ones probably we're most familiar with are these two here, Proxima Centauri and Barnard Star. These two stars I will be coming back to a little bit later on. So the spectral types as well is worth mentioning, the OBAFGKM. We can break those down into sort of subcategories as well. So for example, the M-class stars can be broken down from M0V all the way up to M9V, which is our smallest source stars. Okay. So what powers a star? Well, I'm hoping those of you that are in the Astronomical Society will know this, and if you have stumbled across this video from other sources, then we're looking at nuclear fusion within the star. That's what powers the stars, what gives the pure energy out of light and heat. And if we're talking about stars in the main sequence, we are looking mostly at the fusion of a isotope of hydrogen, whether it be deuterium, tritium, tritium, forming together to make helium. So in the red dwarf star, same things that we see happening. We see hydrogen fusing into helium. Now, because it's much smaller, there's going to be less gravity, less pressure, and therefore the rate of fusion is much slower. The rate of fusion very much depends on the size of stars. So when we talk about very large stars, so O-class stars, they could be white dwarf stars. So if we look at our hypergiants or our blue giants, we're looking at stars that are fusing through their material much, much quicker. And the stars that are fusing at a smaller rate, like our M-class dwarf stars, they therefore will emit much less light. Okay, less fusion, less conversion of that sort of that nuclear energy, that potential energy within the nuclei of those atoms being converted into light. So, again, sort of nailing down into the red dwarfs, you can see there's a vast variety in the brightness of those. So the largest is around 10% of the sun's luminosity, and the smallest is around about 0.0001%. So this is starting to give you some idea about the challenges behind observing red dwarf stars. By very nature, they are small. That is hence their name. And as they're small, they emit less light. And because they're small and they emit less light, they are challenging to observe in the vast cosmos that is our universe. But let's have a look at the life cycle of general stars, just to give a bit of an overview. Here we can see the life cycle of a star. So we start off with our nebula here in the middle. And if it's a star like our sun, it will go down this way here. So we form our main sequence star there. And then over time, it will expand, become a red giant. Those outer layers have left. What then forms a planetary nebula. Again, I know I said we keep naming simple. We did originally think that maybe this is where planets were formed from, but now that's probably not the case. And then what's left behind is the core of the star, which is effectively a large lump of carbon that's radiating heat, no more fusion going on at all, and eventually will radiate heat out into space, and eventually will stop emitting light and will become what we refer to as a black dwarf. And now if we look at much larger stars, the mechanisms that are going on here is we get these much bigger stars forming, and we'll talk about those on the main sequence in a bit anyway, to give us a bit of comparative. And obviously they will go through the same expansion process, but obviously a much bigger size. So we call these super red giants or red supergiants. And because of the sizes and the forces involved, this causes a sort of a rapid contraction and collapsing, which results in a supernova. And again, depending on the size of the mass, depends on if the protons and the electrons get fused together to form neutrons, or if actually we go a little bit further and we cause this black hole where essentially the large mass of the star is getting squeezed into a volume of zero, then creates a super dense state known as a black hole. That is a talk for a different time to go into the life cycle of the star, but essentially they all start from the same place. They all start from a nebula. We've got a lovely image here of a nebula, and depending on how much material there is, depends on how big the star is. So the more material that happens to be in a localized region, the bigger the star that can form as it collects more and more material. So what is the main difference between a red dwarf star apart from the size, apart from the colour? Is there anything different in the structure? Would we expect a red dwarf star to follow the same sort of path as our sun? And it is possible. And just out of interest, if you want to know what nebula this is a S106, which is a star forming region. So the difference with the red dwarf is because it's smaller, it has a slightly different structure to it. And as a result, it means the life cycle of a red dwarf will be trillions of years long. Our sun will have a life cycle roughly around 10 billion years, but a red dwarf, we're talking trillion. So much older than the current age of the universe, which is around 13.8 billion years. So if we look at the sun, we start off with the core region here. Then we have what we call the radiative zone. So this is where heat will transfer by the process of radiation. Then we get to the convective zone, where we get the cyclical transfer of heat up to the upper layers, the photosphere of the star, and then it cycles round in what we call these convection currents. That is what our sun would look like, and we believe these convection currents are what cause things like our sunspots. And so we think the convection zones influence the magnetic field of the star, but also that transfer of temperature. We know these sunspots are much cooler. So if our surface of our sun, say for example, is 5,500 Kelvin, then the black spot here, which is a sunspot, will probably be around 3 to 3,500 Kelvin. So we know it's got to do with temperature regulation, and we know the effect it has with magnetic field as well. As these sunspots are quite intense regions of magnetic activity. Now here we can see the red dwarf star. Now from our analysis of a red dwarf, we believe they are fully convective. So you have convective core as well, no radiative zone, full convection occurring across the whole star. Now this is important when we come back to look at the project a little bit later on and at what this influences. What this means really, if we said that this convective zone is responsible for the sunspots on the surface of the sun, then obviously it doesn't take much to assume that if you've got a fully convective star, you're going to have a lot more star spots. Obviously calling them star spots now because it's not on the sun, but it doesn't really matter. So here we've got much more activity going on the surface. Been much more interesting than the sun has been recently over the last couple of years. Where I think every time we do an astronomical event to have a look at the sun, we see nothing. But there'd be a lot more activity on the surface, and we think this would cause the very strange and powerful magnetic fields that we see on the surface of the red dwarf. As a result, red dwarfs seem to be quite unstable. And that instability causes a lot of flare activity and an awful lot of, like I said, some star spots earlier. And it's that flaring activity we're going to look at in a second, and the star spots will come back to that a little bit later on. So where do they sit on the HR diagram? This is a classical example of the HR diagram, which you may have seen before, and it's referred to as the Hertzsprung-Russell diagram. Two guys came up with it independently. Hertzsprung and Russell collaborated. It's essentially a scatter graph. They've taken the luminosity and the surface temperature. You could also plot magnitude on one side. You can see they've got temperature and colour down here and classification. You could put multiple things on the same axis and still get the same pattern. This line going through here, we call that the main sequence. So these are where stars will spend the majority of their lives before then transferring over into the giant stages and then either supernovaing, although, sorry, that would cause it to go in that direction because it would get instantly brighter, or maybe coming back down to white dwarfs here for the smaller stars. And obviously you can see our sun is here, and our sun will go through that process of going to the giants and then down to the white dwarfs. The stars that we're really looking at today are these ones down here. And you might see a few that you recognise there. I know it's a bit blurry, but Gliese, 775A, 725B. We've been looking at a lot of exoplanets in that region, and I'm going to go into that in a minute. Now, for something which is so small of this diagram, you might be surprised to know that actually red dwarfs make up about 71% of the entire stars in our galaxy. In the universe. Not only have we observed that in our own galaxy, we've observed it in other galaxies as well. Now, we know that less than 1% of the entire mass of the universe is made up of stars. And of that 1%, we're saying 70% are red dwarfs. So the question is, why is that important? Why are these red dwarf stars are important? And the hint is here. Now, one of the biggest areas of research at the moment in astrophysics is the search for exoplanets. Why are we searching for exoplanets? Because we want to know that question that everyone asks when they meet an astronomer. Do you believe in aliens and so on? We're looking for extraterrestrial life. We're looking for the possibility of life existing in the universe and answering that question of, are we alone? Now, red dwarfs, if they are 71% of the stars in our in the universe, then we need to be looking around those as well for planets as well as other systems. And it could be, now that we think that every star has at least one planet around it, these stars can actually be quite forthcoming when it comes to looking at the data for exoplanets. So, one of the regions that we need to look at is the Goldilocks zone. Now, the Goldilocks zone, or known as the habitable zone as well, is all based about the liquid state of water. So, as Goldilocks broke into somebody's house, the criminal that she was, she tried 3 different types of porridge. She tried Papa Bear's porridge, which was far too hot. She tried, I can't remember if it was Baby Bear or Mama Bear, but that was too cold, and then the one in the middle was just right. And that's the same concept with water. If it's too close to the star, the water will boil away and become in a gaseous state. If it's too far away, the water will be frozen and be in an ice state. in a region just in between, the water should be in a liquid state. And that's the basis of our understanding of life. We believe that water is necessary for the existence of life. And as a result, that is what we're looking for when we're looking around for planets. So if we have a look at these regions for a variety of different stars, you can see that hotter stars, this green region here represents the Goldilocks zone, is quite far away. For sunlight stars, it's okay. But then when we get to our red dwarfs, it's much, much closer. Now, one of the main methods that we use at the moment for identifying exoplanets is something called the transit method. Now, the transit method is where we have a star and we have a planet that goes across the face of the star. As it goes across the face of the star, as we measure the light levels coming through, we notice a drop in the light levels. That drop signifies that planet going across the surface of the star. And so if the star is smaller and the orbit is closer, potentially we would see these dips much more often to represent a shorter orbit, and we might see quite a significant dip if the star is already quite small and if the planet is quite large. So if we're talking about massive stars and tiny little planets, that's going to be a really hard amount to measure, that drop in light. And assuming that we can already measure the light from that star, from the red dwarf, noticing a drop will be really, really important. So we have confirmed, I think I checked the other day, is about 3,130 exoplanets have now been confirmed. These Jupiter-sized ones are quite rare. These are very large gaseous planets, just like our Jupiter, hence the name. And actually, when we're talking about the red dwarfs, we are looking at them probably being tidally locked because of that closeness to the actual star itself for that region to exist. They could be tidally locked. And the issue with tidally locked means that as the planet orbits around the star, one side will constantly be facing the star and one side will be constantly facing away, which means you could have one surface boiled alive, one surface absolutely frozen. And so even with being in the habitable zone doesn't necessarily mean that guarantee of liquid water. However, if we took that planet and we had our region exposed to space, so the dark side, and the region exposed to the star, then this region in the middle, along the boundary, would potentially be a perpetual twilight, where the temperature would be cooling enough for life and water to exist. So it is even possible that on some of these planets we may see a band of life in existence rather than in these hot or cold regions on either side. But there are other things we could be looking for that could give the possibility for life to exist, and that would be things like a very thick atmosphere. But the atmosphere formation can be very difficult if you've got one side that's constantly being boiled and given a lot of energy from the sun, and the other side being frozen. But a thicker atmosphere would allow for the formation of convection currents and allow that heat to disperse across the surface, but it would mean that you'd have a constant atmosphere. Another possibility is an ocean planet. If you had a planet covered in water, then the water could potentially act as a barrier to that the heat from the star. Okay. Okay. So, I mentioned earlier about the convection regions of a star and how they cause strong magnetic fields. And so those strong magnetic fields cause quite a lot of flaring. And as you can see here in this animated GIF here, you can see a flare coming off of a red dwarf star there. And we observe a lot more flares within a red dwarf than in other stars. Now these red dwarf flares are highly energetic. In 100 years that we've been observing the sun, we've observed maybe one or two of these sorts of flares. In a region of about 10 hours, astronomers observed a couple of red dwarfs. They observed 18 separate flares on each of these stars to give you the same equivalent energies. So to give you an idea, there's much more activity on the surface of a red dwarf than there would be on our sun. And what does that mean for potential life? Well, it wasn't that long ago, in 2016, that we discovered Proxima Centauri b, a planet going round Proxima Centauri, our closest star, so potentially our closest exoplanet. Only 1.3 parsecs away, far too faint to be seen with the naked eye, and about an eighth the size of the Sun. Now, that discovery was quite exciting because it actually put within grasp the potential ability to visit an alien planet outside of our solar system. And this planet looked to be in the habitable zone as well. Unfortunately, in 2018, as these stars can be very temperamental, that we saw a flare so powerful that we could actually observe the star with the naked eye. And that flare, unfortunately, was directed directly towards Proxima Centauri b. So if there was any life existing on the surface of that planet, it would have been wiped out by the energy of that flare. So this could tell us something about the likelihood of life around red dwarfs. It is possible that the activity and the proximity of these planets would be that life might be impossible to grab a hold on the surface of these planets due to the immense energy being radiated by these flares. However, we know where there is a will, there is a way, so this might have led to interesting evolutions that we one day might observe. Now, another fairly local red dwarf would be Barnard Star. Barnard Star you might recognise from some science fiction novels from the 70s. Featured quite a lot in a lot of novels about the potential of life. And obviously we have discovered a Jupiter-sized planet as well, orbiting around Barnard Star in that habitable zone. That's what the HZ stands for there, is the habitable zone. We think the Barnard Star is about 7 to 12 giga-years old, bearing in mind the age of the universe is about 14 giga-years. It would have formed very early on. And we see this orbiting around very, very quickly. You can see there the luminosity again, 0.03% of the Sun's luminosity. Very, very challenging. However, although it is in the habitable zone, it's a little bit like Mars. It's just past the snow line, which means that it is unlikely. I'm sorry, I do correct myself. The habitable zone in this area, on this star, was much smaller. It's about maximum of 0.1 AUs, and this was found about 0.4 AUs. So it's past the snow line, and by that we mean obviously the water then becomes ice and in a solid state. So therefore, we don't think that is hospitable for life, but we could be wrong. So a couple of other stars that we may be familiar with: Gliese and Kepler, Gliese 581c and Kepler 186f. NASA produced these fantastic sort of 1930s style travel posters that you can see here on the right. And there what they're showing is that because of the peak of the light being in the infrared, obviously life here on Earth, as we saw, was the peak was in that green-yellow boundary. Vegetation here on Earth has evolved to photosynthesize green light more efficiently than other colours, and therefore chloroplasts here on the Earth are green. It could be on a planet, say, orbiting around a red dwarf star that has vegetation, that those chloroplasts have evolved to be red in colour. And so when we go to a planet orbiting round, let's say planet F around Kepler 186, we'd see this beautiful red vegetation of red grass, red trees. Certainly gets the imagination going, which is quite exciting. So, if we have a look at this very exciting slide of what the issue is what we have observed is that the observed radii of the M-class dwarfs don't seem to match up with what the theoretical evolutionary models show, especially where the orbital period between binary red dwarfs is less than 1.5 days. And now, it could be the fact that they're within a binary system is what's causing these discrepancies, and that's what we're going to be looking at. Now, the reason why we use double eclipsing binaries, that's what DEB stands for, that should be a smaller s, but double eclipsing binaries is because what we find with the double eclipsing binaries is that they've not reached the Roche limit. Now, the Roche limit is where the gravity of the large body is strong enough to prevent any smaller body being held together by gravity. So here you can see the smaller body approaching the Roche limit here, and as a result starts breaking apart, and then it would sort of migrate towards the surface of that star. This is very similar to what we see in type 1a supernovas with white dwarfs and a progenitor. So because they're not approaching the Roche limit, rather than having distorted shapes, so for example, if we had a red dwarf approaching the red in a binary system with another red dwarf, and they were reaching the Roche limit, at the Roche limit, what we would see is actually sort of a teardrop forming of the red dwarf, as matter would start to transfer from one star from the smaller star to the larger star, and that shape would then distort our data. So the ones that we're looking at give us quite perfect round shapes, and as a result, that gives us a very nice light curve. So that drawing I showed earlier for the transits, where we see a dip, those are light curves. That's what we're looking at. When we see those light curves, we can make good measurements. Okay. So what are these possible causes of this difference between what we'd expect to see in the radii and what we're actually measuring? Now, I spoke earlier about how there are intense magnetic fields on the surface of a red dwarf, and we believe that is caused by the convective zone, but also the fact that as they're orbiting round on the smaller periods, it will cause a faster rotation. That faster rotation, just like an ice skater when they've got their arms held out and then they bring their arms in and they spin around faster, that is kind of the same thing here. As they get smaller periods, we see a faster rotation. That faster rotation could lead to the two stars being tidally locked, so facing the same side to each other at all times. And that combination of magnetic fields could cause a much stronger magnetic field, causing greater disturbances within the convective zones of both the stars. And those difference in convective zones could then cause a continuously changing magnetic field. The stabilizing effect of the magnetic field could change the internal structure of the star. And if that internal structure changes, then obviously the radius and the size of the star will change as well. So this is one possible cause. Another possible cause is the red dwarfs. Is the star spots on the surface of the red dwarf. Now, I said earlier about how the convective region will drive the star spots. Now, as the star spots come to the surface, what will happen is those are cooler regions. These are all cooler regions of the surface. And if there are lots of star spots on the surface of the star, that will reduce the effective temperature of the star. And to conserve flux, the star will then increase in size to make sure there's a conservation of energy. So as the surface temperature decreases, to conserve that luminosity, that flux, we would get that increase in size. That increase in size could be that discrepancy that we're seeing, and we need to build this in as a factor as our evolutionary models. The other thing as well is the inaccuracy when it comes to the metallicity of stars. Now, when it comes to astronomers and it comes to the structure of stars, we have found a way to simplify the periodic table much simpler than Mendeleev. So rather than putting it into columns and all that, we've kept it quite simple. We go hydrogen, helium, metals. That's right, as astronomers, everything that's not hydrogen, helium gets classified as metals. And there is a link between the age of the star and the metallicity ratio. Okay, so when we look at what we call the Fe to H ratio, the Z to H ratio. So we're looking at the amount of elements compared to hydrogen as a comparative to see how old it is. And you can see here that the much older stars are sort of shrunk into a much smaller region. Okay, so how have we compared the models? Now, we have multiple satellites and observing stations collecting data all the time. And that data is then used and collected. So, for example, this is this very 90s looking website, and I think they've had to go back to an older version of the website. The version of the website I used was much more modern looking. However, this is BASTI, and BASTI stands for the Bag of Stellar Tracks and Isochrones. Now, those isochrones are what gives us those evolutionary models. And I use the data from the Kepler telescope, which was launched in around 2004. and that's collected an awful lot of data on evolutionary models of stars, and so that is used as my comparative point because the sample size of the data was very, very large. When you're selecting the data for doing the comparable for the evolutionary models, there's a few factors you've got to select, and I selected no overshooting, no diffusion, and for no mass loss. And that overshooting is what we see happening within the convective region into the radiative zone. So when you've got a destabilization between the boundary between the convective zone and the radiative zone, you'll get some overshooting of the convective zone into the radiative zone, which can cause a bit of destabilization and will change, obviously, the evolutionary model of that star. However, when we're looking at red dwarfs, they're fully convective, so we can ignore the overshooting. Now, when we talk about the diffusion of the star, we're talking about the atomic diffusion. And the atomic diffusion of the star influences the direction in which the evolutionary model goes. And so if we get in the deep interior, the helium sinks towards the core, that can effectively lead to a faster aging of the star. So again, we're talking about red dwarfs here, a very slow rate of fusion. So again, we've assumed no diffusion. And mass loss happens in much larger... You get mass loss in any star. However, the mass loss in much smaller stars is much, much, much smaller, obviously. With larger stars, they get to a size where actually the energy being generated out by the star is enough for the outer layers to get a certain amount of mass loss pushing away from the star. Whereas with the red dwarfs, it's much, much smaller. So, initially, the first starting point is this assumption true? Is what we see from the star from our observations, does that vary with what the theoretical models show? And we can see, yes, it does. The blue here shows the model. This shows the relationship we should see between the radius and the mass, and we can see that goes along that line there. Whereas here, the orange shows the observations. And you can see that's a much higher line. I know my line's not great there, but you can see it's a much higher line. And that is being determined by the difference we're seeing in the radius. And we can see here that it does seem to vary a little bit more for these masses as we approach 0.5. However, this is a model looking at red dwarf. So very much my research sort of focused down at this tiny little end here, trying to pull that data apart. So the next step from that was to determine about the relationship between the period and the difference in the observed radius. Was there a pattern? Was there a relationship between the period, the orbital period, and the difference in the radius that we saw? If there was a pattern, there could be a more logical explanation that maybe just the track of the path of the evolution that we assumed was slightly incorrect. As you can see here from this lovely scatter graph, no, there was no relationship. However, what we did see when we compared this to longer periods, so say periods greater than 1.5, is that we saw the scatter between the difference in radii representing a much larger range than larger periods. So when we got the period longer and longer, which meant the distance between them was larger and larger, then the difference we saw in the radius reduced to almost within the error margins, so those error bars. Here on this graph you may not be able to see the error bars are very, very small, but here you can see even just the range of the difference in radii goes from all the way up here to all the way down here. Okay, so we can see there's quite a large difference in range there, and we don't see that at the higher end. So it seemed to show and I used open source data here, and when I did the standard deviation of this of these results, because I thought, maybe there's a slight relationship in that direction. When you did the standard deviation of this, the number came out very low and didn't show any significant relationship. However, I did seem to establish that there was a much bigger difference at a period less than 1.5. Definitely established there was a difference between the radii I've observed and the theoretical models, and that was essentially the heart of the research I did, was taking open source data sets which are huge, and a variety of different scientists use them for different parts. I use maybe part of this subset, part of that subset. I used 3 different sets of data and used the subset to collect enough data on a variety of stars are represented red dwarfs. Obviously, when you're doing these dwarf measurement surveys, they're quite large, so you get anything ranging from M class to K class stars. And obviously, for me, the main focus was on those M class stars. So I had to extract quite a lot of data and then simplify it down to then collate it in this system. So it was very much established. That was the aim of the project, was to establish whether or not there was a discrepancy. And if there was a discrepancy, how much was that discrepancy? Was there any relationship between the orbital period and the difference in radius? Which, sadly, I got to the end of, and the answer was no. Obviously, if there had been a relationship between the orbital period and the difference in the radius, this would have led to quite an exciting sort of avenue of trying to work out what that relationship was and how that would have affected the evolutionary model. Sadly, as the way is with science, and not everything is about exciting discoveries. Sometimes it's just about reaffirming what we believe, and that's what this has done here. Now, I think it was maybe a week before submission time, a paper was released by Han et al. Looking at the issues around some of the data collected so far. So, having spent all this time working on this project, it almost got taken away from me at the last minute. So, Han did extensive research on 3 double eclipsing binaries, and he actually came to the conclusion that the discrepancy was caused by the accuracy in the data. He did extensive near-infrared measurements using space-based telescopes and found that actually the data was more in line with the theoretical models than previous studies had suggested. Now, near-infrared is able to get through the opacity of the atmosphere. We can do a lot of near-infrared measurements here on the surface of the Earth. So the atmosphere will play an effect, but it's a minor effect. It shouldn't cause huge inaccuracies in the data. But Han argued that because of the small size of the stars and the limited amount of luminosity that we're observing, that actually any sort of error that's added to that can cause that discrepancy in the data that we are observing. Now, the Earth-based telescopes, we used a combination of photometric and near-infrared readings. So there was this possible fly in the ointment, which, as you can imagine, got me down a little bit as I got towards the end of submission. However, the key thing is there were 3. And throughout this project, you always have to accept the possibility that there is a limitation on data. However, there are only 3 that he's explored with this, and we have a data set which is huge for double eclipsing binaries from space-based telescopes and from here on Earth. His argument was that he used high resolution, but until we've got more data set on that, the possibility of the instability caused on the surface is looking more likely at this point. Obviously, as a scientist, you never say with certainty, but it's definitely looking more likely. Now, here we can see that the next one was the actual age metallicity errors. This could be quite high. It can actually be up to 10 to 15% difference, and depending on the distribution of the stars, the energy distribution, we can actually get a metal poor stellar population looking very similar to a young metal rich star. And this was highlighted initially by Renzini and Bisoni in 1986. And it's referred to as the metallicity degeneracy. So there are known issues with the with the metal age sort of relationship. However, a more recent research project has managed to reduce that error down to 3 to 5%. And actually, even taking that 3 to 5% in, this doesn't seem to be as big an issue as we once thought. And obviously, this limited data set I've put here is linked back into what Han et al. Was saying. He was arguing that the age of metallicity is what caused an error as well, but having now reduced that error down to 3 to 5%, it's within an acceptable range. So, whilst I at first reading this paper, it caused absolute despair. Walking away from it, thinking about it, analysing what he was actually saying, looking at the limited data set, realising that the age metallicity error had been reduced massively already in a previous study. It led me to take this with a pinch of salt. It was a good suggestion. It has a lot of potential, as you may have seen in the articles that I've put in Pulsar. I've regularly addressed this and bared this in mind, and the next few years should hopefully give us more data on this. So, in conclusion, what I discovered was that there was a more significant disparity at short period orbiting binaries, and in fact, actually, we saw almost double the difference in the radii than we observed at periods greater than 1.5 days. After 1.5 days, we actually saw that difference sort of getting much closer once we did further analysis of the data. So in terms of the orbital period, the smaller it is, and again that seems to link back to the idea that actually this faster rotation will cause that combination of magnetic fields, and it could be a mixture of the two. The star spots being becoming more active as a greater magnetic field disturbance. It could be that it's a combination of those two factors that have led to this conclusion. We also found that there was greater disparity between higher masses than lower masses stars. So again, higher masses have a slightly higher magnetic, or would have a higher magnetic field, and therefore cause more disturbance. So if we had a high mass binary system, then those magnetic fields would be quite would be large and would interact with each other quite massively. However, I do acknowledge that we need more data, especially for low mass stars, and that has a high signal to noise photometric data. And the one thing that Han was arguing was that he wanted high resolution infrared spectroscopic and photometric measurements, which, being on Earth, the resolution would be lower than if it was in space. So obviously the next step is to take it to space to get more readings from space telescopes, and from there develop it. But we've got lots of telescopes out in space at the moment which will be able to support that. TESS has now been launched. We've got the James Webb Space Telescope going up. All of those will add to the data sets that we've got, and then this can be revisited. However, there does seem to be a discrepancy, more than it can be just discounted for possible inaccuracies in the data. And it looks likely that it's a combination between disabling magnetic fields caused by short periods and the combination of those magnetic fields, and potentially as well that causing more star spots, and with that conservation of flux causing a slight increase in the star. That seems more likely at this point. However, like I said, more data is needed. Well, I hope you've enjoyed that sort of whistle-stop tour through red dwarfs. There'll be lots of more videos coming. I think me and Ian have our work cut out for us. So you'll be seeing our faces a lot more, hopefully. For those Astronomical Society members, I will be on the Imaging Wednesday meeting if you want to ask any questions about red dwarfs or a little bit more about the data. And hopefully you've read the Pulsar articles, and I've tried to keep keeping the science in it, keeping those a little bit more easy to read. And if you have any questions and you're not a member, first of all, you can join up or just email the society, make it for the attention of James, and I'll get back to you. Thank you very much.